So now we're going to start talking about another important category of functions called logarithmic functions. Let b denote a positive constant not equal to 1, then f of x equals b to the x is a one-to-one function. Now, this is an exponential function. We're still talking about exponential functions right here. An exponential function is a one-to-one function. Its graph satisfies the horizontal line test. So I graphed the general shape of an exponential function when the base is greater than 1. And just recall that the domain is all real numbers, and the range is the interval from 0 to infinity with 0 not included. So this function, this exponential function, has an inverse function. And the inverse function is called the logarithmic function base b. And it's denoted in the following way. F inverse of x is equal to, the way we read this as, we say log base b of x. So I'll write this here, log base b of x. And because it's the inverse of the exponential function, the domain of the exponential becomes the range of this inverse, and the range of the exponential becomes the domain of the inverse. So here's the domain and range of this logarithmic function. Now, probably the most important thing to learn right now about this new notation is the following, what's in this box. Y equals log base b of x means x equals b to the y power. This log notation can be kind of intimidating and confusing at first, and so we're gonna spend some time translating, rewriting log equations and log expressions into exponential form. That's a good way to just get a handle on what a log means. In fact, even for me today, sometimes when I encounter a logarithm expression, I rewrite it as an exponential to get some sense out of it. So that's what we're going to practice in these exercises. And we want to be able to, again, take a logarithm expression, like y equals log base b of x, and rewrite it as an exponential. So we need to get the base, the exponent, and the number on the other side of the equal sign in the right place. So in A, where we have log base 10 of 1,000 equals 3, if we want to rewrite this, keep in mind that 10 is the base, that we say log base 10. So when I write the exponential expression, my base is going to be 10. I'm going to be writing 10 to some power. The number by itself on one side of the equal sign is always the exponent when we switch to the exponential expression. Sometimes I draw a little curve from the base to the other side of the equal sign because that helps me remember 10 to the third power is what I'm talking about here. 10 to the third power equals the number inside the logarithm, 1,000. And okay, now it's not so mysterious. Of course, 10 to the third power is 1,000. That's the exponential form of the logarithm in part A. Now let's do B. Log base 3 of 9 equals 2. The base is 3. The exponent is 2. So we're saying 3 to the second power equals, the number inside is 9. 3 to the second power is 9. Makes sense. So we're not actually calculating anything here. Again, we're just converting to exponential form and trying to see if what we're writing makes sense or not. It should make sense. Part C, log base 25 of 5 equals 1/2. So I would take the base 25 to the 1/2 power, 25 to the 1/2 power should equal the number inside, which is 5. Now this one might not be obvious right away unless you think about the meaning of the 1/2 exponent. 1/2 exponent means take the square root, take the positive square root of 25, that's equal to 5. Oh, I got it, of course, that makes sense, right? And one more here, just with some symbols and variables involved. Log base W of P equals Q. No numbers here, we just have to rewrite this as W to the Q power. So that's saying W to the Q power is equal to what's inside the logarithm is P. So log base W of P equals Q is another way of saying W to the Q power equals P. Now what we'd like to do is change the direction, take some exponential expressions and rewrite them in log form. So each one of these we're going to convert to log. And now how do I start converting this to log form? Well, the subscript, the b base, is always the base of the exponential. So my exponential base here is 10, so this is log base 10. And it's always going to be of some number equals the exponent. The exponent always goes by itself on one side of this equation. So log base 10 of something equals -2. The something is going to be this number here. Log base 10 of 1/100th equals -2. So notice the base ends up as a subscript. The exponent on the base ends up by itself on one side of the equal sign. Okay, let's try another one of these. 2 to the 10th equals 1024. So it's log, what's my base here? My base on the exponent is 2, log base 2 of a number will be 10 goes all by itself on the other side of the equal sign. Log base 2 of 1024 goes inside. So here the number on one side of the equal sign goes inside the parentheses. The exponent on the base in the exponential form always goes by itself on one side of the equal sign. C, let's do another. We got log, my base is going to be the base of the exponential, which is log base 16. And the 4 will go inside, equals the exponent goes by itself on the outside. 16 to the -1/2 power is 4, or log base 16 of 4 is -1/2. One more with symbols. C to the k equals z. We're going to write this as log base c, because c is the base on the exponent. The exponent goes all by itself on the other side, k, and inside parentheses goes the z. The parentheses is not always written, but so it's, I guess I'd say it's optional, but sometimes it just makes it easier for me to, when writing by hand, to read these things. Okay, now we're gonna do a few simplifying exercises where these expressions can be expressed in a much simpler way, and we got to figure out how to do that. A is log base 3 of 81. What I like to do is I'd like to take that log base 3 of 81. And set it equal to a variable. So we're going to set it equal to x. The reason I do this, I create an equation that we can now translate into exponential form. So I set the log expression equal to x. Now I'm going to translate to exponential form. Base 3 to the x power. What we have is 3 to the x power equals 81. We need to find x. The hope is that when we write this exponential form, it will be easier for us to figure out what's going on with these numbers. One way to figure this out is to try to write both sides with the same base. Over to there. Writing both sides with the same base. Now I know I got 3 to the x equals 81. 81 I know is 9 times 9. But each 9 can be thought of as 3 times 3, right? So 81 I can think of as 3 to the 4th power. 3 times 3 times 3 times 3 would be 9 times 9 is 81. So I can replace this 81 with 3 to the 4th. Now, why would I do that? Well, if I have 3 to a power on one side, 3 to a power on the other, if I have the same base, then the exponents are going to be equal. Then x, the exponent here, has to equal 4 the exponent on the other side. And that's my answer. Because we were trying to find x. I'm gonna have room to squeeze it in here. I'm just going to write log base 3 of 81. That's what we were trying to simplify in the first place. That's equal to 4. That's what we found out. We set it equal to x. We rewrote as an exponential. We were able to figure out what x is, which is equal to our original expression. So that was equal to 4. Now let's try B. Let's do the same thing. Let's let log base 10 of 0.0001 equal x. So set it equal to x, and then we're going to rewrite as an exponential 10 to the x power. 10 to the x power is equal to 0.0001. Now, sometimes you'll be able to just guess what x could be, but one way to get a handle on this is to try to think of both sides with the same base. This is 10 to the x equals 10s, 100,000. That's 1/10,000th. But if 10 to the x is 1/10,000th, 10 to the x is equal to, that's 10 to the -4 power. If 10 to the x equals 10 to the -4, we got the same base. If you got the same base, then the exponents have to be equal to each other. So then x has to equal -4, and that's our answer to this one, our log base 10 of 0.0001, so that was A, B, log base 10 of 0.0001 is equal to -4. Right equals -4. Okay, C. Log base 5 of 1. So I'm going to let log base 5 of 1 equal x. Rewrite this as an exponential expression. The base 5 to the x power is equal to 1. Okay, wait, now how can I need the same base on both sides. Well, I know 1, any number to the 0 power is 1, so I know I can write that 1 as 5 to the 0. I want to get base 5 if I can. I can write 5 to the 0. I have the same base, so then x is equal to 0. And that's what log base 5 of 1 is equal to. Log base 5 of 1 is equal to 0. One more here. Log base 2 of 2 to the 9th. So we're going to let x, let log base 2 of 2 to the 9th equal x. Then 2 to the x power is equal 2 to the 9th. This one's actually already set up for us. That means the bases are equal, so the exponents have to be equal. X has to be equal to 9, and so D has to equal 9. Continuing with a couple more. Log base 27 of 9. So let's let log base 27 of 9 equal x. Then 27 to the x power has to equal 9. Okay, now 9, I don't think of 9 as 27 to a power, but what I can try to do is just break down both sides of this equation. In other words, 9 is 3 times 3. 9 is 3 squared, but that's not base 27. However, 27 I know is 9 times 3, and 9 is 3 times 3. So 27 is 3 to the 3rd power. I can write this as 3 to the 3rd power to the x. So I'm trying to get the same base on both sides. I got 27 written as base 3, 9 as base 3. 3 to the 3x I can write as 3 to the 3 times x equals 3 to the 2nd. Same base. So then the exponents have to be equal. 3x has to be equal to 2. Now here I don't have my answer yet. I have a little bit more work involved to solve. I got to divide both sides by 3 to isolate x. And I get x is equal to 2/3. 2/3 is our answer. This original log expression, log base 27 of 9, is equal to 2/3. Okay, now we got log base 2 of -4, so we want to let log base 2 of negative 4 equal x. So I have 2 to the x equals negative 4. But now, maybe this is my version of a trick problem here. The thing you got to observe is that 2 to the x is never negative. So there is no such value of x. There is no x that works. So log base 2 of negative 4 is undefined. No such number. There's no way 2 to a power could actually be equal to negative 4. That's not negative 2 squared. Negative 2 squared would be positive 4. So here's an example of a log expression that's undefined. Now I'm going to do a few solve for x problems also. And here, notice we already have a log equation set up, so that I didn't have to let something be equal to x. X is already involved. I can go right to rewriting these in exponential form. The base to that power, 3 to the negative 1, is x. 3 to the negative 1 is a third. Oh, so that's it. X. What is x? X is equal to 1/3. Part B, 10 to the 0.5 is x. Well, again, that's x. That's our answer. Now, what does 10 to the 0.5 mean? I would probably want to write that as 10 to the 1/2 equals x, which is the same thing as a radical 10 equals x. It's a little bit easier to think of that as the positive square root of 10 is x. One more. 2 to the 4th power. Okay, 2 to the 4th power is x. Again, I've got my x solved for already. 2 to the 4th power is 2 times 2 times 2 times 2. 4, 8, 16. 16 is equal to x.